Hello and welcome to the fourth session called Designing and Printing of Complex Parts. In first three sessions we have shown you how to perform mechanical testing of 3D printed samples, which standard we use for tensile testing in order to acquire best possible material for your 3D printing. Then we've shown you two common 3D printing devices, namely FDM type device and SLA one. In the next session we've shown you how slicer softwares look like, their interface, how you perform process settings for your 3D printer. So if you remember, for FDM type technology we've acquired a G-code file, and for SLA device we acquired certain form file. So those two files we used for uploading them to 3D printers. We've shown you how 3D prints look like in the second session and how you post-process your models. If you remember, for FDM technology we had to remove a raft and supports, and with SLA technology, because it uses liquid plastic, they call it resin material, we had to rinse models in isopropyl alcohol in those two vessels, if you remember. Then after rinsing them we had to cure them with UV light in a chamber. And I've shown you two same models made with an FDM and SLA technology, and show you the advantages of each technology. So with this last session I'm about to show you a complete workflow from beginning to the post-processing of your models, what you have to perform and what you will deal with when 3D printing your complex parts. So 3D printing shows its advantages in manufacturing of complex parts when it is hard to attain your model with conventional technologies. But for 3D printing you need to have your model in digital form. You need to have an STL file to work in your slicer software. So first you have to attain your model, either by CAD modeling or some sort of 3D scanning. First you have to CAD model your model. Then you have to convert it to STL file. You need to tessellate your CAD model to work in a slicer software. In slicer software you generate printing paths for your 3D printer to perform. Then you upload that file to your 3D printer, you perform your 3D printing, and when the 3D print is finished, you maybe have to or not post-process your model to its final look. So a complete workflow I will show you in a example of one particular total hip replacement implant. So from our previous work we had to perform numerical simulation and 3D printing of a certain old hip implant. On picture you see a stem of total hip replacement implant made of one titanium alloy. So this physical model has a complex geometry, and it is very hard to make a digital model using vernier caliper. But conveniently we have a 3D scanning device to make a digital model from this here hip implant. So our 3D scanner has a scanning head, as you see here. It has its table mount, and it is connected to our PC, and turntable also connected to PC. What turntable does is that you place your model onto it. It performs a rotational movement and stops in defined number of times when a 3D scanning head illuminates a model with a UV light, namely a blue color light, and then two cameras, one on the left side and one on the right, record those sections of a model. So, our hip implant is of sort of gray color. It is a titanium alloy, and because we need to have a contrast of our model comparing to this black turntable, now you see it on this here picture, I've covered a titanium implant with a Teflon white tape. So, how does a 3D scanning look like? So, here you see turntable turns and stops. Scanning head illuminates a blue light, and during that time two cameras record a section. Then it will continue doing the same thing in the next section. Let's look at the longer video. So what you see here on my computer, you see slices which 3D scanner makes. This is the first window defining our process in 3D scanning. So I have to define exposure of light, how long it will be, and it will define the resolution of our 3D scan. Then the next option is how many scans it will perform, making a one circle. So when a turntable makes one circle around, it will stop 14 times, and I'll have on my computer 14 slices for preparation. So let's look at the whole video. It makes a slice. Now it made next one. It illuminates a model. Turntable turns for the next section. It stops. Now next illumination and scanning. Our 3D scanner works, has a software convenient for SolidWorks CAD package. These are regular options in SolidWorks, and we have for our 3D scanner an additional card called Geomagic for SolidWorks. Our particular 3D scanner is called Geomagic Capture X, and it uses this software addition for SolidWorks. So first what we did was scanning, and that window before on that video opened with a pushing of this button scan. Then these slices, if you've seen in the previous video, are aligned using the Align Object and Optimize Alignment options. So when you finish aligning them and making a whole surface model, then what you do is merging them. When clicking merge, a software makes a cloud of points looking like this. it has a ununiform density that is just a cloud of points defining geometry of this here total hip replacement implant. So when you have a point cloud, next you have to make reference axes and planes in order to acquire your CAD model. So before that, you have to region your point cloud with this here option I'm showing you. Instead, I'll show you what we made. This is how we regioned this point cloud. Every other color shows the next region on the model. So this is how a program partitions this point cloud. After that, you make axes you need. So here I have an axis for these two cylinders of stem neck. Then planes. You make planes on flat surfaces using regions program defined. So just for an example, in this plane 3 here, I've selected the green region and this gray one, and with selecting them both and clicking on plane, I've acquired a plane that is planar with the bottom surface of this collar on this hip implant. So after doing all the axes and planes you need, step by step you make a CAD model. I'll show you a complete model. So when I uncheck my point cloud, you see the model we made in the software. Now I'll check a mesh, one again. I'll uncheck region. So you see they are somewhat similar. To see how much your CAD model differs from your point cloud, you have this deviation analysis option. I'll show you our results. So this is a picture of our deviation analysis. We had maximum deviation of 1 millimeter in excess and about 1 millimeter in some areas less than point cloud. Okay. We'll return back to the SolidWorks software. So, by having this CAD model, I'm show you the saving of the model. So, your model is in a format convenient for your particular CAD software. So here we have .prt or solid part to save our model and use it again in SolidWorks. Here you can choose a file format you want to save your model. So when you're using this model for slicer software and then 3D printing, you'll save it in STL file format here, and the model will be tessellated. I'll save it on desktop, clicking save, and now it has tessellated it. All bodies, yes. And now let's see here. this is how a model looks like, and it is ready for slicer software. And by using these instructions for the third session, you can make a file for 3D printing and print it and post-process this here model. The best convenient technology for model like this, if you are considering FDM and SLA technology, of course, is SLA one, because of the greater dimensional accuracy. You can rapid prototype this model, or you can use, when printed, you can use this model and test it in laboratory to see if the geometry is convenient, or you can save that file in STEP or IGES format for numerical simulation in, for example, Abacus. So here are some results we had. We considered a thickness of this implant. So the thickness is 14.6 millimeters. We used a standard loading for maximum loading for implant, and we had this stress state results in one side and the other one. We made some corrections in the program. So in the CAD we've lowered the thickness of the neck, and again imported that model in Abacus software to see how a implant would perform on maximum load. And now again to 10.4 millimeters, and the lowest thickness of implant we've considered was 9 millimeters. So here are these two pictures showing the stress state when a neck thickness is 9 millimeters. So what I want to point out here is that with 3D printing you can easily redesign your model, fast prototype it, see the flaws, then make changes in your CAD software, save it as STL, and again print it or consider it for numerical simulation, or compare the 3D printed sample for laboratory testing and a model in numerical simulation, and compare the results from numerical and laboratory testing. Okay. Now I'll close this file. I won't save it. So to point out that your STL file can be of CAD model origin, or there is a other type to acquire your STL file. Just for an example, in dentistry, a newer type of dental models are acquired with 3D printing. So this is a standard dental model for making dental crowns. It is a standard casting method. To avoid that and to shorten the workflow, you can scan a jaws of a patient using the intraoral scanner. Here you see a intraoral scanner scanning teeth of a patient, and behind you see a program showing scan patient's teeth using an intraoral scanner. Here in this video you see a dentist using one intraoral scanner for mapping patient's teeth. Behind the patient on a laptop screen you see an open software for 3D scanning, and on it you see how 3D scanning performs. So after scanning of a upper jaw, a dentist scans a lower jaw as well. And after that procedure, he sends that collected data to dental technician's office. This is a screen from a dental technician's office. So after acquiring a model from a dentist, they insert few parameters, and a program sends as an output an STL file for 3D printing. After that, and that STL file is used for 3D printing on SLA 3D printing machine, and based on that dental model they make dental crowns. So here in this workflow you don't have a creation of a CAD model. So between a point cloud and a creation of a file in STL format, you don't have any CAD modeling. So in this here particular software, it skips creation of a CAD model. Even if you could make a CAD model, it would be almost impossible concerning the geometry of the teeth. So a particular company made a software which skips creation of a CAD model. So in dental technicians' practice, they don't have any creation of surfaces, planes, axes, and so on for creation of their STL file. Okay, next I'll show you how a dental model looks like. So this one is printed using a gray resin in SLA technology. So the models on the right side is antagonist, and on the left is a working model with a teeth on which a dental technician creates a dental crowns. So on the next picture you see on the right side a model without pillars, and on the left side this is a complete model with a bridge. This here is a bridge construction on which holds two pillars, and the third component with the frontal pillar to see the biting of upper and lower jaw. Again, one other dental model. So in dental practice you don't have any creation of CAD model. Again, some 3D printed models might be used in an assembly. Maybe you have to create a functional part that will be used in assembly. So the geometry of your part has to be has to have right dimensions for the other part in assembly to work with your 3D printed part. So here on this here picture we have printed a camera holder, and here you see a 3D printed model with raft and supports. On the next picture you see a post-processed part and its functional use. So it is mounted on a stand for camera, but between camera and a stand there was no holder available for them, so maybe camera was of some different manufacturer than the stand, so they are not compatible with each other. In that order, we had to make a middle part for a camera to be holded and a stand to hold camera in an assembly. So in some sort this is an assembly, and this is one example of 3D printed parts that have functional use. I'll show you one example, the other example as well. Here on a picture I'm about to show you, are teeth placed in a holder. So here you have almost 50 pieces of incisor teeth, all which have adequate holders for one testing. There was one demand from dental school to test incisor teeth which were in a solution, and to compare them with incisor teeth that were not holded in a solution for a particular amount of time, just to see the influence of that solution liquid on performing of incisor teeth. So here we had to make holders to hold teeth in vertical position. Each of the holders is different to hold different teeth, of course. Some of them had geometries that were very easy to attain with vernier calipers. Some of them, like the upper incisors, had to be 3D scanned. Okay. Now I'll show you in SolidWorks what I am talking about. So we've attained a 3D scan of the upper incisor. Here you see a surface of a 3D scanned tooth. Okay, we perform scanning, aligning and optimizing of the scans. We've done the merging, so you see a point cloud of a particular tooth. And with reverse, and now to make a holder, we had to make many cross sections of this particular tooth using planes and attaining cross section of teeth. I'll show you some. Okay, 1, 2, this and that one, and that one, that one, that one as well. Now I'll close a mesh so you see what I am talking about. You have cross sections at 1 millimeter height from another, and this all was used to make a tooth holder for this particular use. So this is some kind of an assembly. So you have a part which is used to hold a tooth. I will show you a tooth point cloud in a CAD model of tooth holder. So I'm showing you a point cloud of a tooth. So you see how a tooth stands in a particular holder. You see there is a slight gap of 0.2 millimeters between tooth and a holder. That is where a cement will be filled for better fixation of tooth to holder, to hold it firmly in a vertical position. So this holder is a CAD file. So it's a solid part in this here case, and a tooth is just a point cloud. So using a point cloud of a tooth, we were able to make an adequate holder for this here tooth. So we had 4 upper incisors, all of which we've 3D scanned. I'll show you those models as well. So this is the first tooth. Now the second one with its holder. You see how a holder looks like. I'm opening a point cloud of the next tooth. This tooth as well has a 0.2 millimeter gap for fixing cement. Now the next one. Okay, you see that all the holders have this slope. So we had to cut one piece of a holder in a model because cameras for mapping strain fields of a tooth during the loading procedure were placed below. So for them to map a certain areas of teeth, we had to make these slopes so that the cameras could map the strain fields of holded teeth. Now the last one. So it's tooth number 12. And this is the fourth holder we've attained by using 3D scanning method. Alright. And now just a second. This is a picture of a G-code, generated G-code of our holders. They were all printed together with a 0.1 height resolution of printing. You see we've used raft, one big raft holding all of the 50 holders for teeth. Each one of them differs from one another. Each one is for a particular tooth. In this here picture I've shown you previously are all the printed holders with a numbers of teeth which they are holding. A 3D printing founds its functional use in dental practice. So on this here next picture I'm showing you how a form file for SLA 3D printing looks like for dental models. So you see two dental models of upper and lower jaw and teeth that are for making of a crown. So each one of these teeth have its own place in the jaw, so that the technician could make a crown on the teeth, and then by inserting a teeth with a mounted crown onto a jaw, a dental technician could see how his crown looks like on a patient's jaw. Does it have any grip with the neighboring teeth? Is the crown too small? And so on. So he can see how his crown will look compared to the other teeth. Now, making of dental models is not just only for dental use. We had one particular case that one food industry needed this dental model for measuring a bite force during a chewing of their products. So on this here picture you see a dental model mounted onto a upper tool of a universal tensile testing machine, a desktop one, so a smaller type machine to measure forces of about few hundreds newtons. So here in Serbia 3D printing has this sort of application as well. Now next I'm about to show you are some new materials used in SLA technology. So not only that you can fabricate models for rapid prototyping, and the resin materials not only differ in color but in mechanical properties as well, and they differ in their function. So particular technology, I mean SLA 3D printing technology, has a wax model available as well. So using a wax type resin, you may make a positive of a structure you want to mold. So in this here particular case, this is for dental use. So here you see a dental crown already made from a wax material. So after, the next thing to do is to make a cast for this here tooth and cast it with ceramics. There is one new application with SLA technology that is making a crown directly as a ceramic. So there is some resin material that has similar properties like ceramic. So you can make dental crowns directly from build platform of your 3D printer. Next, I've shown you how dental model resin looks like. Just a second. Okay, the model is uploaded. So a dental model resin is used for making models with greater dimensional precision and greater level of detail. Now I'll show you the next one, the next material. Next two materials are biocompatible, so they can be used directly in patient's mouth. So I'll import the file. This is a model of dental splint. So for fixing your teeth to make them appeal more beautiful, you use these dental splints to align your teeth better. Some older techniques were more robust and required more time to make. This dental LT material is transparent, so the patient can use a splint during his everyday daily activities. Next material I'm about to show you is also a biocompatible material, and that is Dental SG of Formlabs company. It is a resin material used for manufacturing of surgical guides. So when you need to install an implant for a new dental crown, this surgical guide is used to place it between the neighboring teeth, showing the path for the drill to make for a inserted implant. So same using an intraoral scanner, a dentist scans neighboring teeth, then dental technician uses that data to make this construction and then send it back to a dentist to drill a hole for dental implant using this here surgical guide. This material also is a transparent one, but has greater dimensional accuracy over the previously shown dental LT material. It is for the best considering that a dentist has to make a drill hole in patient's mandible. And that's the last biocompatible material I'll show you today in this session. Next, not only for dental use, but also in biomedical engineering in general, 3D printing has a good functional use. So for an example, when a patient has tumor in his bone, like femur, tibia or such, one easy way to deal with this problem is to make a surgical guide based on a CT scan of a patient. So when a leg or an arm is open, a surgeon inserts this guide and it helps him to know where to cut. Then on the previous place they insert a scaffold-like structure for bone growth. They insert their bone grafts for a bone to be grown again. So this is a new trend in biomedical engineering. Now showing you one example. The scaffolds are mostly made of metal material, but a trend is to make a biodegradable plastic material that will decay in the same rate as the bone grows. So as the final product, you will have a fully grown new part of a patient's bone. Next, using 3D scanning is useful in treating tumor of mandible, for example, because at the middle part of the mandible you have symmetry between right and left side. So when on one side you have a ingrown tumor, you attain a model through CT scanning. Then on the next picture, let's look at that one. So using a program, you cut the problematic part of the mandible, and using a healthy part, you mirror it to the other side, so you have a complete model. And that part that surgeon will cut, based on this here one, a scaffold-like material is printed with a bone, with a plate just used for fixation. In the next part, after inserting bone grafts, in a few months or years time, a patient will have a ingrown bone on the part of a mandible where there was previously tumor. So there are some future applications for 3D printing. For today, I think this is more than enough to show you about designing and printing of complex parts. So I think this is enough for this session. Thank you for your attention and have a nice day.